a WikiVidi documentaries production. Don't forget to like and subscribe. Enjoy. Annihilation. In particle physics, annihilation is the process that occurs when a subatomic particle collides with its respective antiparticle to produce other particles, such as an electron colliding with a positron to produce two photons. The total energy and momentum of the initial pair are conserved in the process, and, more generally, are distributed among a set of other particles in the final state. Antiparticles have exactly opposite additive quantum numbers from particles, so the sums of all quantum numbers of such an original pair are zero. Hence, any set of particles may be produced whose total quantum numbers are also zero as long as conservation of energy and conservation of momentum are obeyed. During a low-energy annihilation, photon production is favored, since these particles have no mass. However, high-energy particle colliders produce annihilations where a wide variety of exotic heavy particles are created. The word annihilation may also be used informally for the interaction of two particles that are not mutual antiparticles. Some quantum numbers may then not sum to zero in the initial state, but must be conserved, with the same totals in the final state. An example is the annihilation of a high-energy electron antineutrino with an electron to produce a. If the annihilating particles are composite, such as mesons or baryons, then several different particles are typically produced in the final state. Production of a single boson. If the initial two particles are elementary, then they may combine to produce only a single elementary boson, such as a photon, gluon, or a Higgs boson. If the total energy in the center of momentum frame is equal to the rest mass of a real boson, then that created particle will continue to exist until it decays according to its lifetime. Otherwise, the process is understood as the initial creation of a boson that is virtual, which immediately converts into a real particle plus antiparticle pair. This is called an S-channel process. An example is the annihilation of an electron with a positron to produce a virtual photon, which converts into a muon and anti-muon. If the energy is large enough, it could replace the photon. Electron-positron annihilation. When a low-energy electron annihilates a low-energy positron, they can only produce two gamma-ray photons, since the electron and positron do not carry enough mass energy to produce heavier particles, and the creation of only one photon is forbidden. By momentum conservation, a single photon would carry non-zero momentum in any frame, including the center of momentum frame, where the total momentum vanishes. Both the annihilating electron and positron particles have a rest energy of about 0.511 million electron volts. If their kinetic energies are relatively negligible, this total rest energy appears as the photon energy of the gamma rays produced. Each of the gamma rays then has an energy of about 0.511 mega-electron volts. Momentum and energy are both conserved, with 1.022 mega-electron volts of gamma rays moving in opposite directions. If one or both charged particles carry a larger amount of kinetic energy, various other particles can be produced. Furthermore, the annihilation of an electron-positron pair into a single photon can occur in the presence of a third charged particle, to which the excess momentum can be transferred by a virtual photon from the electron or positron. The inverse process, pair production by a single real photon, is also possible in the electromagnetic field of a third particle. Proton-antiproton annihilation. When a proton encounters its antiparticle, the reaction is not as simple as electron-positron annihilation. Unlike an electron, a proton is a composite particle consisting of three valence quarks and an indeterminate number of C quarks bound by gluons. Thus, when a proton encounters an antiproton, one of its quarks, usually a constituent valence quark, may annihilate with an antiquark to produce a gluon, after which the gluon together with the remaining quarks, antiquarks, and gluons will undergo a complex process of rearrangement into a number of mesons, which will share the total energy and momentum. The newly created mesons are unstable, and unless they encounter and interact with some other material, they will decay in a series of reactions that ultimately produce only gamma rays, electrons, positrons, and neutrinos. This type of reaction will occur between any baryon and any antibaryon consisting of three antiquarks, one of which corresponds to a quark in the baryon. Antiprotons can undo annihilate with neutrons, and likewise antineutrons can annihilate with protons. As discussed below, reactions in which proton-antiproton annihilation produces as many as 9 mesons have been observed, while production of 13 mesons is theoretically possible. The generated mesons leave the site of the annihilation at moderate fractions of the speed of light, and decay with whatever lifetime is appropriate for their type of meson. Similar reactions will occur when an antinucleon annihilates within a more complex atomic nucleus, save that the resulting mesons, being strongly interacting, have a significant probability of being absorbed by one of the remaining spectator nucleons rather than escaping. Since the absorbed energy can be as much as 2 gigaelectronvolts, it can in principle exceed the binding energy of even the heaviest nuclei. Thus, when an antiproton annihilates inside a heavy nucleus such as uranium or plutonium, partial or complete disruption of the nucleus can occur, releasing large numbers of fast neutrons. Such reactions open the possibility for triggering a significant number of secondary fission reactions in a subcritical mass, and may potentially be useful for spacecraft propulsion. Higgs production. In collisions of two nucleons at very high energies, C quarks and gluons tend to dominate the interaction rate. So neither nucleon need be an antiparticle for annihilation of a quark pair or fusion of two gluons to occur. Examples of such processes contribute to the production of the long-sought Higgs boson. The Higgs is directly produced very weakly by annihilation of light quarks, but heavy or C or produced quarks are available. In 2012, the CERN laboratory in Geneva announced the discovery of the Higgs in the debris from proton-proton collisions at the Large Hadron Collider. The strongest Higgs yield is from fusion of two gluons, while two quarks produce more easily identified events through radiation of a Higgs by a produced virtual vector boson or annihilation of two such vector bosons. Brought to you by WikiVidi documentaries. Would you like to know more?